Hey, welcome to the Hackers Teaching Hackers 2021 CTF Solve video series. In this video, we're going to be taking a look at reverse engineering 2, which is called Punch Out. So let's go ahead and get started. All right, so the Punch Out challenge is a little interesting. Punch Out is a binary that we can download here. I've already have it downloaded, and I already have it loaded into Binary Ninja Cloud at cloud.binary.ninja. And you can do reverse engineering of binaries directly in your browser, which is pretty cool. First, I'm going to go ahead and copy this information, and we're going to go and connect to the service just to see what it looks like. So it's presenting us with a punch-out game. It tells us to insert 25 cents. The screen's flashing, showing us Tyson knocking people out left and right. Then asks us to enter one of 10 possible characters. For opponents, I'm going to go ahead and do Don Flamingo. I always liked fighting him. And then we'll do 1. Okay. Oh, crap. He knocked me down. All right, that's not good. Go ahead and connect again. I'll do Don Flamingo one more time. Then I'll do 0. Ooh, he knocks me down. Jeez. This doesn't look like it's going to be easy. Let's go ahead and reverse engineer it and see what is actually going on here. Okay. All right, so I'm going to go to the main function. And when we load things up into Binary Ninja Cloud, we're going to be starting off at disassembly. So this is the native layer. This particular binary is compiled for Linux, so it's an ELF. This architecture is x86 64, which is 64-bit Intel architecture. I'm going to click disassembly, which is going to bring us to low-level IL, which is low-level intermediate language. Then we'll go to medium-level intermediate language, and then finally high-level intermediate language, and then repeat the process over and over again. Intermediate language is essentially taking our low-level disassembly and converting it into a sort of unified instruction set. It doesn't matter if I have an ARM or MIPS or PowerPC or whatever supported architecture, it's going to try to normalize that into a representation that sort of fits all of those things, right? The low level, medium level, and high level are different amounts of analysis that don't necessarily throw things away in between each one. So in a tool like Ghidra, when you do disassembly, you're getting things lifted up into a sort of intermediate, a first set of intermediate representation called P code. It's sort of like a very basic P code. And then there are transforms and analysis done on that to bring it up into like a refined P code. And that form is what spits out or is used to generate that very nice kind of like pseudo C-like. And that's what happens here, except Binary Ninja developers give us access to more levels of that analysis in between so that we can go to the very beginning of that and start to see sort of like the initial analysis process. And then before we start throwing away information and start making assumptions, we can do the analysis on the low level. Then on the medium level, we start to get things like stack resolution. So we get an understanding of certain types, what the stack layout looks like. And then as we start going into HLIL, we start to remove intermediate variables and make things look a lot more like a pseudo C or C that we would develop in, right? Okay, so we basically want to stick with, unless we have a very good reason, with HLIL or high level IL. This is going to be what sort of looks familiar to us if you have C programming experience. So I can click spacebar to go back and forth from this nice kind of block view, which is a control flow graph view, and then space to go back into this linear view, which is more of like what we'd be looking at when we're writing code. All right, so first of all, we have that choose your opponent. I saw this before. I see this srand where it's seeding random, the random number generator, with a timestamp. So this is pretty standard. Every time this program runs, since time is counting up, we're going to be seeding it with a different time every time, or different value, which means that when we call rand, we're going to get a different sequence of numbers coming out of this thing, okay? We're going to clear the screen. We're going to print out some information about our boxers. We're going to get a character. Whatever that character ends up being, we remove 30 hex. 30 hex in ASCII is 0, 31 hex is a 1, and so on and so forth. So by removing 30 hex, we're essentially just being left with what would be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever, okay? So if we have a value that is not, if we have a value that's greater than 9, then we're going to go into the sorry, the boxer's not available, and we're going to seed random with a very specific number. That means if I run this and I can get down this code path, I can pick the number that is passed to the seed for the random number generator, which means every single time I run this binary, the random number generator is going to print out the same sequence of values. So that could be very, very important. This RAX7 is the name for, it's based on the RAX register, so it's given it an arbitrary variable name. So this is basically like boxer choice or user choice or something like that. And then in here, we can actually name that user choice, boxer choice, user choice, whatever. And then depending on what was entered, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, we're going to load up and call the very specific boxer to the ring. That information is essentially stored here, 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 and so on and so forth. Okay. Then we're going to go ahead and get a character just so we put the information up here before inundating them with a whole bunch of other information. Then we're going to print out the actual action list. So this is going to be 0, 1, 2, or 3. It's a dodge, left kick, right kick, those kind of things. Then we're going to have a counter. So we're going to enter an infinite loop. And in that infinite loop, we're going to say if the counter ever reaches above 23, we're going to do roll credits, you win, your flag. So maybe the flag is just in here. Let's go ahead and take a look. We can go to the strings, excuse me. It says roll credits, you win, your flag is the winning combat sequence, HTH, blah, 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 blah. Okay, so the flag is not in here as plain text. We actually need to enter in a set of characters that is going to cause us to win. All right, so I think we need to go down that, that code path that is going to see the random number generator so we can keep running this and find out that sequence, right? There's no way we're going to be able to guess 22, 23 characters in one go. That would be like just impossible or next to impossible. All right, so the next thing we're going to do is find out how this counter updates. So down here, you dodge. So if we dodge, we'll go to this counter. Sometimes these indents can be tough to follow, especially when it kind of cleans this up and doesn't put our curly braces in here, just to kind of keep everything sort of neat and concise. It's almost like Python with the tab delineation. So let's go into the basic block view or the control flow graph view. So we have this true loop. While we're down here, we're going to come back all the way over here and loop back to this and keep going down this thing. If at any point we actually bail from the counter being too large, we're going to do roll the credits and break out of this while true. So that's what we want to go to. If we fail this, we're going to connect and get knocked down, and then we're going to exit. Okay. So we want to keep going down and dodging every single time. And every time we dodge, the counter is going to go up. That means that we're going to be picking the correct action to dodge. The correct action to dodge, since this is the predicate that determines whether or not we get hit or we dodge, will be in combat action. If I go into combat action, it's based on, let's see here, this value, which is the return value, which actually comes from R2 is not equal to this. We're going to have combat modes, comes from artificial intelligence. So this is a return value, but artificial intelligence, whatever this function is going to return a value. It's going to check that with our combat moves, and then it's going to determine whether or not we were successful. Artificial intelligence, as we might have thought, uses RAND. So artificial intelligence, we can actually make artificial intelligence generate the same sequence of numbers as long as we can force the SRAND to, or the application to go down the path where SRAND seeds that same number, a deterministic number. The only other way we would be able to do that is to like wait 24 hours and then launch the launch the application at the same exact time so that the time function generates the same value. Actually, it wouldn't do that anyway. I think it's based on epoch. Yeah, no, I don't think that's even possible. You might have to like reset the system or reset the time. It's just not going to happen. So the only way to solve this is going to be to go down this location. So let's see. We have a switch choice. I like to click around a lot and that. So go down here, all the way over here. Sorry, that boxer is not available. It's actually before the switch. So we need to enter some value to get down to here. Sorry, the boxer is not available. And I think it said if the value was larger than 9. Let's try it. Okay, let's do this. Let's do 10. All right, so we did von Kaiser. Von Kaiser's 1. So when I enter in 1, right, or like 10 or something like that, or 9, so when I enter 10, it's actually just reading the first character and then looking from there. So let's see if I do 11, von Kaiser, and if I do like 20, it's Piston Honda too. So it's only reading the first character. So how on earth do I make this thing actually read anything that's larger than 9? Let's try -1. Oh, ho, 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 ho. All right. So that's interpreted differently. That ends up being a larger number. So the way that we represent signed and unsigned characters or signed and unsigned integers ends up being a little different, which ends up fooling that logic and going to this, sorry, that box is not available. We're sending you in with Mike Tyson, Smarty Pants. So now what I can do is every single time I run this and I get to Mike Tyson, it's seeding RAND or SRAND with 2021. So what I can do is test to see what the sequence of actions is. So I'll say 2. Okay. I connect. I'm going to keep on going. I'll hit 2. Oh my gosh. I connect. Keep on going. Keep on going. Could we do it again? No, I get knocked down. Okay. So I know from here that the first action is 2, 2, 2. And I know that, we call it, I want to keep track of that. So I'll do sublime text. So it said in the string that it would be the correct sequence, right? So it'll be 2, 2, 2, and then something else. So the kind of unfortunate part of this challenge is that you essentially either need to, on the same exact Linux distribution, perhaps. I'm not sure if this would be possible because I don't know what the differences between pseudo-random number generators is or different distributions or versions of Linux. So if this was on like Ubuntu versus some other distro or something, where that delineation is, that would be something that I have to look up and see. You may actually be able to write a small C application, seed SRAND with 2021 yourself, print out the first 23 characters and just use that. But there's no guarantee, I don't think, that it would be the same on the remote system. I think you need to have like the same distro or something. So in this case, what we're going to do is we're just going to play the darn game and try to slog through it. So 2, 2, 2, 3. Oh, keep going. Okay, so the next action is 3. So I can go ahead and write that down before I forget it. And then we'll go to the next one, which is 1. Oh, we got knocked down. Okay. So 1's not correct. And we can keep doing this process over and over and over again until we actually get the flag. I'm not going to do this. I'm not going to do this. It's going to take too long. I'm just going to go into the admin panel, go into challenges, get the actual flag, and just submit it because it's going to take too long for me to do for this particular video. So what was it? Punch out. There we go. Punch out. Punch out. Oh, no. Punch out. Flags. Here we go. This is the actual thing. So maybe we can actually just go through this real fast just to see what happens when this works. All right. You can go away. Let's go. Window. All right. Here we go. Let's fire this up. -1, 2, 2, 2, 3, 3, 2, 2, 3, 0, 0, 1, 1, 3, 1. Oh no, where were we? 1, 1, 3, 1, 1, 1, 3, 1, 3, 0. 1, 1, 2, 3, 3. Imagine if I had to guess all these. Forget it. That wouldn't be possible. All right. Okay. Roll credits. You win. Your flag is the winning combination sequence. Yeah. So that's pretty much it. Go ahead and copy this, and we'll paste it in. It'll definitely work because we got it from the system. Here, punch out that and go in there. This is kind of like one of those fun problems that's like there's just a small gimmick or trick that makes everything completely unfold, and it makes it seem like a really hard challenge or an impossible challenge. is like can't be solved until you see that like one little gimmick, that one little thing that makes it all work. And after that point, it's just just working through the challenge and doing it. So that's pretty much it. Next one, we're going to go to challenge response, which has a very interesting story. So you might want to check that one out. We'll see you then.